Okay, any any questions before we get rolling? Okay, so the last thing, so last time. Yeah. And then I is any ideal can be generated by two elements. And of course, let me point out that if it's a principal ideal, it can certainly be generated by two elements. So in particular, two or less, if it's a principal ideal. But in fact, I has property and this is a consequence of the proof we did, that where A in other words, you can essentially choose the first generator at random, and B, of course, also and I has to be selected more carefully. It's called the 1.5 generator. Called 1.5 generator property. And all density domains have this theorem. This, I'm gonna leave this unnumbered now. Theorem, if so suppose that you have a Prufer domain. I'm not going to prove this one, by the way. And its Kroll dimension is n. Then any ideal of R can be generated by less than or equal to n plus 1 elements. Notice that, of course, a Dedekind domain is a one-dimensional, well, an interesting Dedekind domain is a one-dimensional Prufer domain, and so you recover the result over there. And the ideal can be generated by two elements or less.
We need this ideal to be finitely generated.
Thank you. I meant to say that any finitely generated. Absolutely. So your ideals either can't be finitely generated or they're generated by n plus 1 or less elements. Let me point out that you can have valuation domains of any dimension and all their finitely generated ideals are principal, right? So just because you have an n-dimensional Prufer domain doesn't mean you require n plus 1 generator. You can have Dedekind domains that are PIDs, and they don't require nothing required two generators. So the obvious next question, I think, is, do such things exist where you actually require n plus 1 generators? And the answer is yes. Prufer domains can constructed for any Kroll dimension n that actually do require n plus 1 generators. Okay. So we talked about the class group, last time. Let me give you, an example here. Um, so, Here. Um, okay. A finite extension. Okay, so here we have a finite field extension of the rational numbers. Then the integral closure of Z in F is called a ring of algebraic integers. So, given what we know now about Prufer and Dedekind domains, we have this diagram here. Notice that N is, since N is finite. Notice the ring of algebraic integers, the extension F over Q is fairly algebraic because it's finite, right? Notice that there are, of course, algebraic extensions of Q that are not finite, but rings of algebraic integers are restricted to this. Take R, which is the interval closure of Z and F. And this is what we call a ring of algebraic integers. And we'll look at the quadratic case after a bit, but I needed to find this here. Of course, any ring of algebraic integers is Dedekind. The algebraic gives its Prufer, but we proved, I believe, last time that this in fact is, no, it wasn't last time. We closed the books on it last time. We proved a few days ago that since this is finite, then this is integrally closed one-dimensional in the theorem, so it's a Dedekind domain. But a ring of algebraic integers is a super nice Dedekind domain. I'm not going to prove this here. It requires some number theory, yin yang, that I'm not going to get into, but I will record this because we're going to use it. Theorem. The number notices this. Let R be a ring of integers. Sometimes I'll press the word algebraic. If I say R is a ring of integers, that's what I'm referring to. One of these situations here. Then R enjoys the following properties. And this does not have to be true for Dedekind domains. Number one, recall what this is. This is a class group. This is the invertible ideals modulo the principal ideals. This forms an abelian group. We crush out the principal ideals to kind of get a better look at this. Uh, This is a wonderful result and gives, this is why people care. And this is another one. There is a prime ideal. In fact, infinitely many. In every ideal class. There's a lot of theorems where neither of these are true in general Dedekind domains. In fact, there is a famous result by Claiborne that says, if I walk up to you on the street and give you any abelian group, it is the class group of some Dedekind domain, right? So you can build a Dedekind domain that has that abelian group, the real numbers, whatever you like. However, for rings of algebraic integers, these are always finite groups. And there is at least one prime in every class. In fact, there's infinitely many. In fact, it's even better than that. Because in a certain sense, the universe deals the primes out in every ideal class in sort of a uniform manner. Let me kind of illustrate the second one. So let me look at a couple of examples here. Now here's one we've beaten to death. Now, what do we know about this? So in our travels, we've discovered several things about this. One thing that we've discovered, well, what's one thing that what do we know about factorization here?
It's not unique.
It's not unique. It's not a UFD. And so, what does this mean about class group?
It's not trivial.
That is correct. Remember our observations from last time with the Dedekind domain. For a Dedekind domain, which this is, UFD is equivalent to PID, correct? And so if it's not a UFD, it's not a PID, that means that there's some non-principal ideals floating around. So the class group has to be non-trivial. So let me. That's true, right? It can be trivial, it can't be because there are ideals that are not principal. And of course, we've seen some of these like, we've seen these interesting animals here. These are all examples of non-principal primes here. Anybody want to take a guess at what? Well, I mean, by this theorem, it should be fine. Anybody want to guess what the structure of the group is? Actually, it is E2, this one. It turns out class number of which is the order of the class group, is 2. By the way, here's a word of caution. If you look at some number theory books, especially in tables and stuff, they will sometimes say the class number of the quotient field of this, which is sort of ridiculous because the quotient field is a field and PID, blah, blah, blah. what they really mean when they talk about the quotient, the class number of a field, is they're talking about the class number of the integral closure Z in that field, right, the ring of entity. Now, up to isomorphism, how many groups of two do you all know? Right, so if you hear me now and believe me later on this, then okay, so what does this mean? I think it's useful to think about what this means for the class number to be Z2. So what does this mean about non-principal prime? What's their behavior? Right, even, that's correct. But even more than that, if I give you two non-principal primes, any two non-principal primes, and multiply them together, it becomes a principal ideal. Any two principal ideals you multiply. So there's a prime ideal in every class. Well, there are two classes here. So here, it turns out, are some coset representatives. By the way, can anybody think of a prime as principal? Not three, right, not three. I'll show you a way to find a bit of these, right? Let me do some computation here. Recall if uh, the norm can anybody see a principal prime? Anybody find a prime element? You see a way to make this prime? What's the easiest way? How about that, right? If you plug in A equals 0, B equals 1, you have 5, right? So the principal class, you see another way to make this prime? How about, oh, I don't know, A equals 6, B equals 1, right? 36 and 5 is 41. Turns out this is a principal prime too. There's lots of ways to do this. I guess I can make this. These are all, and in fact, any principal ideal would represent a coset, but these are primes. All of these are primes in here because they've got a prime norm and they're irreducible, and you can argue from there that they're primes. As a matter of fact, this particular ring, you need a little bit more than that.
You just need prime number, even though it's not a UFD.
Yeah, for this ring. Oh, yeah, if the norm turns out to be a principal prime, that means that it splits into two elements, each with that prime norm, right? So what happened to the prime is it split into two principal primes, and those principal primes have to be So, non-principal. And you know what, we can use this actually to show it. Also. Let me try this here. Yeah, let's do this. What's the norm of that? Okay, so now I'm factoring two-digit numbers. I hope I do something more significant in this graph as I'm teaching on the next line, otherwise I feel a little stupid. 3 factors this way. We've seen this earlier, that if you think of these as ideals, this is P3 times P3 bar, that's the ideal. Is there an element of norm 7 here? Can you write 7 as a square plus 5 times a square? Now you can exhaust that pretty quick, right? I mean, you can't let B be 0 because 7 is not a square. And if B is 1, well, that doesn't work because 2 is not a square. And if B is anything of absolute value bigger than 1, then you're out of luck, right? Because that means that there should be a prime ideal. 7 should factor this way. So whatever P7 is. And in fact, if you look back at our proof, can anybody think of generators for P7? If you think back to the proofs that we did, my solution here will not be unique. That should work. And again, that's not a unique solution, but that should work. This is kind of a 1.5 generated property. If you look at the prime ideal factorization of this, this is P7 bar. And the factorization of this is, right, did I do that right? 27. Yeah, that should be right. This should be, actually, that should be. So what do you think about this? Hold on a second. This is on this, so this should be, and that should be 7. Yeah, that's right. So this should be this element right here. This is the norm of it. The norm of this should be one of these, right? Because the norm is multiplicative across the ideals as well, right? So this thing right here factors this way, and so if you look back at the proof of what this is, this should be P7, right? It's generated by this, and P7 bar and P3. Now, I could have this wrong. So what happens if I have, what happens if this is P3 bar P7? well, then this should still work. Right, because again, the common factor is P7. But what happens if this is P3, P7 bar? What happens if I got that wrong?
So far.
Yeah, then what this would do is this would necessarily, using this as the other generator. Right, the constant of it. Because, if this one is equal to this, then this one will be P3 bar, P7, and then I'll get my common factor of P7. Alright, so for example, if you give me that this thing is, class number Z2, which it actually is, give you kind of another example. Let's do something like this. So if you have, oh, this is, yeah, there it is. The norm of this is what? 145? Right. Now, how do you factor that into integers? Well, this is 5 times what? 29. So this is divisible by radical -5, because as an ideal, and how about 29? Can I write 29 as a square plus 5 times a square? Actually, I think I can I? And I'll write this as, uh, '29. All these are principal primes, so actually this element here, 145, this norm, actually factors in this ring as a product of 4 primes, 3 of distinct, right? This squared up to a unit, this squared, this times this. Everybody okay with that? And so actually, you can recover this one here. Because notice, you can use the norm to sort of backtrack. I guess it is sort of obvious that you can, the norm has this. This tells me I should be able to pull at least one of these primes out. And there we go. So notice what we've done is prime times prime. So actually, this element that I picked here is sort of at random, actually factors uniquely into primes here, as opposed to something like 6. And so you can use these norms to kind of get it down to primes and figure out whether that prime is principal or whether it's not principal, based on whether you can represent something as a square, 5 times something square. So that's one kind of application for this. But the interesting thing about this ring is you've got the principal class, you've got the non-principal class, right? And then when you multiply any ideal that's not principal times another ideal that's not principal, you get an ideal that's principal. So for example, let me give you an example. And this is kind of a little bit of a magic trick here. X squared. Somebody give me a prime and make it interesting, you know, I don't, please not too many digits, but give me a prime that you can't write in this form. Any prime that you can't write as seven. Seven cannot be written in this form. Everybody agree? Can't write a square. Give me another one. Well, I think another prime that can't be written as a square. What's 5 times 13. Um. I like this house. You have to be really careful about this. Let me do this. Let me. Computation. There are other, we gotta be careful here. Let me ask you a question about these 2 primes that you gave me here. Are either of these primes still prime? And how will we test that?
If they generate a prime ideal.
Okay, right. So, do they? All right, let's look at 7. And let's see if we can generalize what we do. See if we can generalize this and figure out a way to tell if a prime is still prime, let's say. So let's suppose 7 divides AB, right? 7 is prime if it must divide one of them. Okay. Well, let's suppose we have is it possible to have 2 things multiplied together to be a multiple of 7 without? Well, let's see here. What does it mean for this to be a multiple of 7? It means that both coordinates, and when I multiply this out, both coordinates have to be 2 plus 7. Do I agree with that? So let's see what happens when I multiply this out. This is AC minus 5B. And then I get AD plus BC. Well, so this would mean that AC for this product to be, should be equivalent to 0 mod 7. And AD plus BC equal to 0 mod 7. Suppose this is true, right? Um, Now, is there a solution to this? Where, I mean, if 7 actually is prime here, if 7 is prime here, then somehow this should imply that A and B are both 0 mod 7, or C and D are both 0 mod 7, right? Let's assume A and B are not equivalent to 0 mod 7.
A and B.
Yeah, that's right. Assume that neither one of them are. So what can we get from this? There's your line. Well, if A and B are not 0 mod 7, I can divide out, right? So I'm gonna divide both of these by A, and so I get a new set of equations. I get C.
Wait, how do you know that A is not 0?
I'm assuming that, and I want to see where this goes.
I thought you were assuming that A plus B root -5 is not a multiple of 7.
No, what we're assuming is this product is, right? I'm assuming this product is multiple of 7, so I get these two equations here. Now let's assume that neither A nor B, so suppose they're both not 0. Oh, I see what you're getting at. We need to assume that only one of, let's assume that A is not.
Oh,
0.
when I ask.
Right. So let's divide by A, and I get C minus 5 lambda D equal to 0 mod 7. And dividing by A, I get D plus lambda C equal to 0 mod 7. Where here lambda is equal to B over A. So I'm for a fraction all the time. So let's see what we can do by combining this here. I get C. I'm gonna replace D by minus lambda C, right? Because really, I'm just doing this. This is basically me doing manipulations in the field, right? I'm doing this in C mod 7, which is the field. So this is going to be C minus 5 lambda minus lambda C. So what do we get here? Well, I get C times 1 plus 5 lambda squared. If I did that right, it looks like I did. Everybody okay with that? What can we conclude from this? One possibility is either C is equal to mod 7. Fine. Or that has to be 0. So that is to say lambda is minus 1/5. I'm sorry, lambda squared is minus 1/5 mod 7. Anybody know what minus 1/5 is? Well, 5 times 3 is 1, so I guess that's negative 3, which is 4. Does that have a solution? Yes, it does. It's got lambda equals 2 as a solution. So, what can we conclude from this? The second one, of course, the first one has a solution. The second one has a solution. What can we conclude from this? Well, so what was E for A? So basically what I need is B to be twice A.
Couldn't lambda also be 5 on 7?
Yeah, that's right, but any solution will work. This can be a solution because, for example, if I take A to be 1 and B to be 2, then this, and there's your 5 hypothetical solution. What happens when I multiply this? I get 21, which is divisible by 7. So 7 still a prime? No. You can generalize this by, you can basically tell it's prime uh, that's you know, off the word was, if my 5 is not square. In C1. See if you check that for yourself, right? So if you go with me with this condition, let's go back to our example. You all gave me 7 and 13. This one was not prime. What about 13? Is minus 5 a square mod 13? I think it's not. We can check this stuff. I mean, so I'll do this, you know, the lazy person's way. Just see if it shows up. What's minus 5 mod 13? It's 8, right? What happens when I square this? 0, 1, 4, 9, 3, 25 minus 13 is 12, 36 minus 26 is 10. Oh, I don't have any more to check. Why do I not have to check anymore?
Negative A squared.
That's right, 7 is negative 6, et cetera, so it should reverse the thing. Does negative 5 show up? Does 8 show up? No. So. This so. This is prime. Do I agree? Okay, try again for me. Give me another prime. See if you can give me a prime that's not a square. Oh, so I want something that you can't represent
Yeah.
there, right? Can you represent 17?
No, but I don't think, I guess that's all you care about, so you can't represent it, right?
Well, then we'll have to check if minus 5 is a prime.
17, 37.
Well, let's try 17 first. Would everybody agree that 17 can't be written as a square plus 5 times a square? Now, is minus 5 in square? Same way, 0, 1, 2, 3, 5, 6, 7, 8. I guess minus 5 is equal to what, 12? This is 0, 1, 4, 9. This is what, 17. This is 16. 25 minus 17 is 8. 36 minus 34 is 2. 49 minus 34 is 15. 64 minus, I guess that would be 51 is 13. No 12, right? So this one's not a square.
37 can be written that way, and it also isn't a square.
Also, but can you find me one where it is a square?
Grandma.
So I'm looking, so last two have been not a square. Can you find me one that's written that can be written this way, but is not a square, or is a square, my bad. How about this? All right, how about, well, 3 is boring. I want one thing to be 3. But I think just any problem that can't be, that cannot be written in that form. Uh, 11. Everybody agree that 11 can be written in that form?
Yeah.
But it's minus 5 the square mod 11. Okay, I don't think that's gonna work.
No.
Can you write 19 in that form?
Then negative.
Well. Okay, so that's gonna be, that's your exercise for next time to find somebody, if it exists, right, or prove it doesn't exist. I want you to find me a prime. With the following problem. 1, P. Right. And -5 is not a square in C. So my P's gotta have these two properties, and you should be able to find one pretty quickly. If you think about this the right way. So any questions?
I do have a question.
Okay,
So we know that for ring of integers, our class group is finite abelian group. Can we achieve any finite abelian group as the class group as some ring of integers?
some ring of integers. That's a ring of integers. Let me check on this. I think the answer to that is not known, whether it can be done. I think, but I mean, if you look. Yeah, and there are certain restrictions based on, I think you can't do it, so if you restrict yourself to quadratic fields or something like that, there are limitations. But, if you're gonna allow me to do any ring of integers, I think that is not known, but, let me check on that. Okay, other questions? Okay, I've got a bounty out, so you all have to wrangle up the one, and I'll show you a trick next time, and we will continue. Any questions? We'll see you on Friday.